Okay, so our second talk is going to be given by Calum Braham, and he's going to talk about continuum models of kinetic tiny particle systems.
Thank you. Okay. Thank you for having me. Yeah. So this is, as it says, we'll be looking at continuum models of kinetic particle systems, and specifically for systems with short-range interactions and clustering. And this is work I've been doing towards my DPhil at the University of Oxford, supervised by John Chapman and Maria Breen. Okay, so what is the problem we're looking at? In general, we're looking at when you have an individual-based, like microscopic kinetic model, which can describe a whole range of physical systems, but specifically, in this case, we're looking at a kinetic model. So, second order here, we have generalized sort of forces in the affecting the change in velocity in time, and these are influenced. These are determined by some kind of interaction potential. So you can see here, this is a sum over all the other particles. J, which is like something which these other particles are doing to influence our particle. And specifically, we're looking at short-range interactions. So that means the particles, I'm going to say generic particles, because these can be all sorts of things, so it's getting fairly abstract. They're only directly influenced by others in their immediate vicinity, which can be used to model a very wide range of physical systems. For example, you might think some animal collective behaviour models might fit under this umbrella, or maybe a traffic model, or people walking in a crowd, or something like that, where sort of you're only getting information from other individuals nearby to you. That's the main idea there. But we can't just use these individual-based models, as I'm sure all of you well know. These can often be intractable analytically, and then computationally nearly impossible if the system is too big. And often we're interested in sort of general characteristics of these, or sort of population averaged properties. And in those cases, it's very common to try to derive a macroscopic continuum model. So the example here, we're looking, in this case, our main aim of the project is to describe the time evolution of these single particle population average probability densities. So the primary approach to keep this in your head as we're going through is we're trying to go from individual-based models to these single particle probability densities in a generic case for these short-range systems. Yes?
I'm a little bit confused by this form of K that it only depends on the absolute value of xi minus xj, because it can't.
Yeah, so we're focusing here only on symmetric interactions on the way through there, where it just depends on the distance between the particles.
The force should take into account what is the.
Sorry, what do you mean? So force.
I mean, the interaction potential might be symmetric, but then force gets the direction. No?
It may do, but that's not. Okay, so it could be. I've probably been a bit generic in the thing that that's not going to be particularly. What we'll be looking at today is more the general form of that, rather than too many specific potentials where it actually change. I don't understand in some of them, actually, it would depend on the direction on the way through, and you can add that. Essentially, I should add an extra xi term there to say that it can depend on that, which will then give you the direction. But yes, there are models where you can get directions which depend only on the vi minus vj without the modulus there as well, which will give you a direction as well in some cases. But yes, good point. And then specifically, we'll be looking there. So later on, we'll look at systems where they exhibit clustering, and then we'll do a more general form of probability distribution, which then allows us to deal with clusters which have masses as well on the way through. And so just to get a bit of a picture of this. There. Just to get a picture of what we're looking at, this is the example of a collective behaviour model, which will kind of, this is the Cucker-Smale collective behaviour model in 2 dimensions. So we're looking here at particles which have their velocity aligned to some in their vicinity, and then as they move, they form clusters that move through space like this. So this is sort of the general picture of one of the kind of models we might be thinking about here. So trying to predict how this is going to happen. Right, okay. So how are we going to go through this today? Firstly, I'm going to look at, so we're just going to go through the setup and using a BBGKY hierarchy to define sort of how we're going to define these macroscopic probability models. And then I'm going to look at 3 different techniques we have for producing a closed equation for our one particle probability density. So the mean field, and then our matched asymptotic model, and then the clustering version. And then finally, I'm going to look at some numerical evaluation results of our clustering model to compare it to some simulations, see how it goes. Okay. Okay, so to get started, in general, here is again, I've put down our individual based model there that we're starting with. The first one is an example of a long-range model here. So it has the 1/n scaling. This is common to like avoid the potential getting too big when you take a number of particles going to infinity. And it has a large length scale here. The short range, and then the short range version where we change our length scale to epsilon here, and now it needs to be scaled by 1 on epsilon at the front to imply that as you shrink your epsilon scale very small, that the interaction still means something. So it has to get big enough to still mean something when you integrate over your small region there. Another definition of the short range interaction is defined as the opposite of the fat tail condition. So when you integrate around a d-1 dimensional shell, your space on the way out, you're getting, you get a finite amount. So it's effectively that in combination with the low density of the system, which we're taking here, the Boltzmann gas limit in general, primarily means that you're only interacting with a few particles in your general vicinity. So the end result of this is you're only interacting with a few particles there rather than getting information in the system. Okay, so how do we set up our probability distributions? So we start by defining the n particle joint probability density function, which is now the probability of the system existing in a specific state. So we have capital N particles all the way through here. This is the full joint distribution for your system. And we can define its time evolution using a probability conservation law like this. So we integrate around a small region in our probability phase space and say that the probability in this region must be conserved. And that gives us this equation here. And then, okay, so for our system specifically here, just substituting in our equations for x dot and v dot, we end up with this. Again, that's when you substitute it in. Then, in some cases, this can simplify down to the Liouville equation, and that's generally when the system satisfies Hamilton equations and they're conservative, but we're not going to be looking at always at that case today, so we're not going to simplify it down to that. So then how do we get from this to our one particle probability density? We integrate over all the other particles. And so that's where the BBGKY hierarchy comes in. So the hierarchy is a system of n PDEs where you, for example, you would define the K particle reduced distribution by integrating over particles K plus 1 through n, their positions and velocities. And so when you integrate all of them out, you end up with a reduced joint distribution for your K particles. And it turns out, so I said, here, this is the, so that's the domain of all your particles just going over. It turns out that the time evolution equation of the K particle reduced distribution depends on the K plus 1th particle. And so you end up with a hierarchy of equations where P1 depends on P2 all the way up to Pn. So this is only closed if you can solve Pn like the full system evolution in the first place, which obviously is what we're aiming want to do by using our P1 equation. So in some sense, we have to find a way to reduce a closed equation to P1 without using the full hierarchy. As I said, yeah, so we're aiming to define a closed equation for the P1 equation there. So in our case, this is what the time evolution equation for the K particle reduced PDF becomes. So not too much about the detail here, so we're just integrating over all of these ones from K plus 1 through to N. And the nice thing here is we have this divergence form coming in the time evolution, which means that we can cancel all of these terms by using the divergence theorem and assuming that the probability goes to 0 at the boundary fast enough that we can get rid of the boundary terms there. So that allows us to simplify this quite a lot on the way through, and I won't go through all the details here, but effectively what we end up here is with a one-particle time evolution equation, which depends on P2, and a two-particle time evolution equation, which depends on P3 on the way through here, just simple ones there. So you can think of this one here. So this is like an advection term here. So this is the spatial movement here, and then this is some form of interaction term, two-particle interaction term for our one-particle equation. And for the two-particle equation, we have our two advection terms. We have two-particle interactions, and then we have what's effectively a three-particle ternary interaction term at the bottom there. Okay. So now we'll look at how do we actually produce the closed equation. So our methods for doing that for this. So the first method we're going to look at here is a mean field closure. So you can take the mean field limit for large systems, which effectively says that your full system probability you split up just as the product of all one-particle probabilities, which effectively was called the propagation of chaos assumption, and it effectively means that you're assuming that particles that were initially uncorrelated remain uncorrelated on the way through. So in our case, that would mean specifically taking our P2 to be the product of the P1 equations for the two particles there, which is effectively assuming that they're uncorrelated, and they remain uncorrelated. So they remain uncorrelated if they were uncorrelated, originally. And then substituting that in, you can simplify your interaction term here to just involve P1, and now we have a closed equation for P1, obviously given what the actual form of the K is, which you then have to put in for a specific one. So that's our mean field closure. So this is sort of a reasonably standard technique, these ones here. Then now we'll look at a different one, which is the one we've been working on, the matched asymptotic model. For this, and then we're going to use, we're going to derive the Boltzmann equation using this technique as an example. So to outline the approach here, we're going to use an asymptotic expansion in our small interaction length parameter. So this is relying on the fact that the interaction is short range to derive a closed equation for P2 at leading order, which defines how our at leading order what happens in the inner region of our short range interaction. And then we're going to match that with the outer region solution to derive our time evolution equation for P1. So how are we defining our outer and inner regions here for our matched asymptotic expansion? We're defining the outer region for the binary interaction to be where our two particles are much greater than epsilon distance apart, and we can assume that they are independent and uncorrelated, which gives to leading order effectively very similar to our mean field assumption, assuming that you can be when you're far apart, you can be independent and uncorrelated. In the inner region, the distance between the particles is now similar to epsilon, and we can define variables that scale with the inner region here. So as I remember understand. So what happens to our P2 equation in this inner region?
Sorry, this independence assumption, shouldn't there be an additional assumption that you're sort of away from the set of particles which backwards just suffered an interaction?
Yes, we'll get to that. So this is that is a necessary assumption in a certain case. But yeah, sorry, I'll talk about it. Yeah, so.
Sorry, I think I missed some sort of notation, but the K sub 1, 2.
Sorry, yes, so the K sub 1, 2 is, sorry, maybe I missed the definition here. So just yeah, K sub 1, 2 is just the shorthand for the interaction term between particle 1 and 2. So just keeping it very generic there. Yes, so you're right. You also need to assume that in the end, but you can talk about it. So in the so in our region here, so again, you just have a P2 equation. We substitute everything in, and it turns out the leading order solution just involves our vector term and two of the interaction terms here. When you put that in, then this is also okay. In order to neglect our ternary interaction terms, so the ones involving the P3 at the bottom here, we have to assume that our system is low enough density so that epsilon d n minus 2 goes to 0 as this comes in, which is then going to get rid of these bits here. But we also have to assume that particles are leaving the inner region, and we're not in a case where particles are correlated and close to interaction and things like that on the way through to leave it there. So again, we'll come back to that in a second. We have our P1 equation in inner variables here. So what we've done is change this interaction term here to be involved in our inner variable x21. And we can see that this part of the integrand here matches with a term in the leading order P2 equation there. So if we take, so just move those same equations back up again, we have the P1 equation. We can replace the integrand with the what we get from the leading order P2 equation, which gives us this equation for P1. And now using the divergence theorem, we can get this term, and we can rearrange the first term there. And we can simplify that to now be just a surface integral over the surface of our inner region now as this goes to infinity. And so this is, so now we have, okay, so now we've simplified this a bit, but we still have a P2 here in the inner variables. So we need to match this to our outer solution in order to determine, to find a way to actually describe this in terms of P1. So how do we do that? I'm going to do this in the specific case for the Boltzmann equation. So we're going to assume we have a three-dimensional system with unbounded velocity domain. And we're going to assume particles are independent and correlated in the outer region, which gives us this term here. But we're only going to assume this for particles which are pre-interaction, which was mentioned before. So this is like Boltzmann's Satz, which is basically assuming we're only allowed to match to the outer region pre-interaction. So you can only assume they're uncorrelated before that, because after they've interacted, they're necessarily going to be correlated, and you can't match to the outer solution there. Right. So we'll just keep that at the top there. Now, outer region matching. So this is now kind of a depiction of our inner region around a particle x1. It gets a little bit messy here on the way through what you have to do, but we align our axes of our inner region such that the relative velocity v2 minus v1 is vertical there. And so then when the particles they're going to approach, so that there's going to be the particles approaching interaction are going to be on the bottom hemisphere, and the particles leaving an interaction are going to be on the top hemisphere. And what we need to do is we're doing a surface integral over the outside of this inner region as the radius goes to infinity, so as we match back onto the outer solution. And these bottom ones are easy to deal with because we have our assumption that they're going to be independent and uncorrelated. So this, we can just replace P2 going with P1 to the leading order solution there on the way through. So, okay, so what we've done now is we split it into the lower hemisphere and to the upper hemisphere on the way through here. The lower hemisphere we can then replace with P1 times P1 using our matching to the outer solution there. The upper hemisphere, we're still stuck at the moment. And the way this is dealt with in the Boltzmann equation is because it's conservative and satisfies the removal equation, you can say the probability when it's exiting here is equal to the probability on that same trajectory as it entered the inner region. So you can map this probability, you can map this trajectory back and define V2 dash and V1 dash to be your incoming particles, which have the same probability, and then you can define it basically in terms of V1 dash and V2 dash, and then map this incoming trajectory to the outer solution and simplify it there. So now effectively, if we then do one more step, which is to map all of these particles on the hemisphere up to the disk showing the interaction. That's just a simplification there on the way through. It's just sort of technicality to make it look a bit nicer. And you end up with effectively the Boltzmann equation here, or one version of it, on the way through. So that is that's one example of a conservative system here, which doesn't have clustering going through to derive a closed equation for P1 there. Now we'll have a look at what happens when you have a clustering system, and specifically the Cucker-Smale system that I described at the start there. So if you have, okay, so some particle systems do exhibit clustering, and this is where we're going to define as particles' positions and velocities are very highly correlated after post-interaction, and potentially they just stay right next to each other or within some range as time goes on. This invalidates our low density assumption, because even though the overall density might be low, the local density can now be a lot higher. So you can't necessarily assume that there's only binary interactions, and the particles don't necessarily leave the region after the interaction. So this is the Cucker-Smale velocity averaging model we're going to use. So it's a model of sort of collective behaviour, potentially often used for animal behaviour. So flocking, things like that. And what it involves basically is the velocities of nearby particles move towards each other. Let's be J minus VI term here. And that the strength with which they do that is modified by some interaction that's occurring here. This phi given the distance between them. We're going to use a short range modification of this, where we just define this interaction kernel to be short range. Again, to use the one epsilon to make sure it's relevant at the short leading order. But how are we going to use a similar process from before? So because now we kind of make all the similar assumptions. So we have to do basically what the model we've done is that we've assumed that, okay, so in leading order, all their interactions occur at a single point as you take epsilon going to 0, or they're all moving from the perspective of the outer solution. They all happen at a single point. So what we do is we assume that an m particle cluster can be treated as just a larger particle with mass m, rather than as m separate individual particles, which is effectively assuming that the spatial extent of the clusters is small compared with the interaction range, so that you're not having like multiple interactions one at a time with all these m particles. You're largely interacting with them all at once. In some of the models, you may think actually from the original picture I showed that probably doesn't make a lot of sense actually, because you can see that the clusters do span longer than the interaction range. But we thought this was good for sort of a first start and see what we end up getting out of this using the numerical simulations. So technically what we do is on the way through this is we add our mass to our n particle PDF. And then when particles cluster, we label them with sort of the clustered state C. So this is an example of a 3-particle system where the third particle is clustered with the first one. Now we define, sorry, that should be a C, not a B. We define the third particle now just gets a C with the stuff with the first one there. And that allows you to sort of flow through a lot of the machinery that we've done previously with asymptotic expansion using this here. And then specifically, we define our clustered PDF now by just getting rid of these C states and renormalizing by the number of choices with which you could arrange which particle was in which cluster. And it gets a little bit messy, but I will ignore most of the detail all the way through there. So we can proceed similarly to how we did our matched asymptotic expansion through the BBGKY hierarchy. Except now we have to sum over the masses as well as integrating over the positions and the velocities on the way through. As I said, I'll skip the detail, but in the one-dimensional case, we'll obtain this. I've defined this capital D here just to be like the material derivatives, so to just put the advection term on this side as well, just for save space there. What we have effectively, so similarly to the Boltzmann equation case here, we end up with, so I'm also saying about this in one dimension, easier to see. In the Boltzmann case, so we have our particles like in the bottom hemisphere, our particles approaching an interaction here. So this is an interval over the particles approaching. Then we have an interval over the particles leaving the interaction here. And then what we also need is to ensure the mass is conserved. We end up with this extra term here, which is where the particles stop in the middle of the inner region and then effectively cluster. So it's like the two clusters were approaching each other, and then they cluster to make a bigger, and then they make a bigger cluster. And that effectively means, in terms of our inner region, that they stopped in the middle of an inner region and appeared just somewhere else in the outer region because they're now only one cluster there. They stop. So this is the extra term you need there for mass conservation. And again, I haven't gone through the specifics of what goes on here, just a bit messy, but we'll leave that there. Then, okay, so how does this look through our Cucker-Smale system? How does this look for the Cucker-Smale system? If we assume it's spatially uniform, so we define our P1 without the X to just be P1 multiplied by the total size of the X domain. And then in the interest of simplicity, our scale and velocity domain, scale and probability, and scale and time. So that looks a bit nicer at the end. But this is effectively what we end up with here. So similarly, we have this first term, which is particles. You can either think of it as particles approaching an interaction or particles being lost to an interaction from your outer region. Then you have these two terms, which are particles appearing from an interaction when they actually leave the inner region. So in this case, for this model, this is where two particles brush past each other and their velocities get closer together, but they don't actually cluster. So they still leave the inner region as two separate particles. Or you have this final term, which is where two particles, the clusters approach each other and become a cluster. So they don't leave the inner region, they become a bigger cluster. Yeah.
Sorry, the capital N and the epsilon are in this scaling again related by the Boltzmann scaling, or are you taking a different scaling?
Yes, I take the Boltzmann scaling.
So it's still low density.
It's still low density overall. But
yeah, locally it might be very
but we don't take the one on N out the front. Still taking the one on epsilon here and not one on N in this case. The one on N is now absorbed into the time scaling effectively there on the way through. So the more particles there are, the faster this is going to happen, but we scale the time. So yeah, so effectively the term sort here is like, it's almost becomes like a population balance model here, where you have the loss of terms due to interactions, the terms which slide past each other, and then the production of bigger particles due to clustering. Okay, that's probably enough derivations. I'll just show you what we find out when we do this model numerically. So yeah.
When you look at the scaling that you have, why are there in the limit still particles which get trapped in the middle? Shouldn't they all get clustered in for epsilon going to zero, the interaction being so strong?
Yes, that's a good point, actually. I think maybe that one. I think if they, sorry, I think the interaction is not infinite.
But in the limit it is, right? 1 over epsilon.
But the integral over the interaction is not infinite. So it's defined. So I think. So the way I've gone through this is that I'm actually concerned now like if the 1 over epsilon makes sense there, but the way I've defined it on the way through was, or the way I've assumed it's working on the way through and the simulations is that the interaction is so I'm not actually taking epsilon all the way to 0 when we do this. That was sort of the derivation on the way through. It's non-zero. Yeah, I'm trying to think whether it still makes sense for actually to be 0 and then this to be a non-infinite integral across the region. In any case, on the way through this, the total interaction is defined to be a constant. So as you shrink epsilon, the total effect of a particle passing through each other is a constant.
Sorry, my mistake. I think you take the gradient. The k is already the gradient of the potential. You don't take the gradient with the scaling, so the let's say the exchange momentum per collision is still of order 1.
Yeah, so that was one thing.
Yeah, my mistake.
So yeah, so the point of taking that scaling is so that exactly the total effect of the interaction is order 1, and then so you can take that. So how do I do this? Maybe I'll, in the interest of time, I'll speak about some of the details here. So basically, I've implemented the particle simulations in Julia, and we define our clusters using a DB, that's called a density-based scan from Scikit-learn in Python. Basically, it says that 2 particles are linked if their positions are within some epsilon or some tolerance, and the velocities are within some tolerance, and then overall we get all the connected components of this, so we have lots of particles linked in a row. So that's what allows you to, for example, define all these particles as a cluster, even though they're not all within the interaction radius, because this one's linked to this one, linked to this one, linked to this one, all the way through like that. So that's one thing there. And generally we use an exponential kernel defined like this, and this is now scale, so epsilon's 1, and we take epsilon to be 5 interaction radiuses, radii, and velocity on that. But then we had to define a new stochastic model because that was fairly computationally intensive to run lots of particle simulations like that. So we defined a new spatially uniform stochastic model, which we use to approximate that with lower computational burden, which extends the range of parameters we can say something useful about. So how did we do this? We defined in 1 dimension the expected interaction rates based on the relative velocity and the size of your 1-dimensional domain. So this gives you, like, assuming that sort of could be anywhere uniformly on this is the expected interaction rate. And this also assumes no spatial extent of the clusters, similar to the cluster assumption, because like if the clusters got very big, then that would kind of reduce the effective domain and but we're assuming that not like that. And now this kind of simplifies to what we had before. So if our velocity difference is greater than a certain quantity here, that's the terms where they just zoom past each other, and the velocities get closer, but they don't cluster. Oops, and this one should say less than that. If the velocity is less than that, then a larger cluster is formed with this mass here. Right, so that, and then we use the Gillespie stochastic simulation algorithm to sort of put all of these processes there. Then, okay, so our point cluster model we implement using a finite volume scheme with a uniform velocity grid and a linear geometric mass grid. So it starts with linear points at like 1, 2, 3, 4, 5, 6 size mass clusters. And then it goes to a geometric grid so that we can go to bigger numbers without getting crazy computational burdens. Just for example, the difference between 1,000 and 1,001 size cluster is much less important than the difference between a 1 and a 2 size cluster. So you spread out the way there. we allocate the so when you interact two particles, they produce a cluster which is going to have their center, which is going to maintain momentum. And then we allocate this to grid points in order to preserve the total momentum to sort of surrounding grid points. That's again implemented in Julia. And we tested all the convergence of the grids here, and basically it turned out we needed to use quite high grid values because in this model the velocities get very close to each other in the end, so you end up with a very sharp distribution, which means that we needed to have an adaptive velocity grid refinement on the way through there to have the velocity grid shrinking as the distribution shrinks. In order to get that accurately, because it turned out that it's having quite an effect on the results. So the simulation parameters we're going to look at, we've got the one-dimensional Cucker-Smale model here, periodic boundary conditions, uniform initial velocity distribution centered around 0. We use our exponential potential here for particle simulations, but I should note that this doesn't really make any difference for the other methods because it effectively gets absorbed into like its total effect, because we're just looking at that sort of shrunk into your inner region. It's just what's the total effect of this interaction, which is then absorbed, this failure, which is absorbed into the time velocity scaling. And again, the particle simulations performed with the ratio of our length scaling to the total domain being 400, but again, that's absorbed into the time scaling for the other models there. So let's show you what something actually looked like. Yes. Here's an example. So this is an example of a velocity distribution over time. So where it says short range PDE here, that's our point cluster model. The mean field PDE is the fields. It says we have sort of right on top of each other here the particle model and the stochastic model here for the velocity distribution. And this steady state is what the steady state should be based on the central limit theorem if you have one sample of, I mean, in this case, this is just a very small system with 6 particles, so we wouldn't expect to do that well. It's just something through. We start with a uniform distribution, samples of 6 particles you'd expect to then have a mean eventually following this normal distribution there, when they all get to their mean velocity. So you can see at early stages, our model does quite well. The point cluster model here, but only at very early stages. Soon it starts to shrink in far too much like the mean field model, and that's effectively because it's effectively doing lots of simulations at once rather than doing them separately, and that it doesn't properly deal with the correlations of the particles afterwards, which means that it then doesn't realize the particles are correlated and keeps them interacting further and further until the velocity gets smaller and smaller. So that's the first thing. Yeah, we get a problem there, but it is still slight improvement over the mean field case, even at these small numbers here. There's a better story with the size distribution over time here, which you can see as the size distribution goes through there. It matches, I mean, not perfectly, but it does sort of qualitatively better than it did with the velocity distribution. And the other things to note here for both of these is that our simplified stochastic model does quite well against the full particle models. So for the larger numbers, we'll just use the stochastic model and not the particle model. So, and I've just said what I've said there. Okay. If we take n to be big, we end up with, we can see this basically. So what I've done here is we've taken this kind of picture here, but for much bigger n, and I'm measuring the variance of these distributions here. Because they're sort of similar shape, except the variance gets too small of our model there. So we're going to reduce this to one quantity, just the variance. And you can see here over time, they decrease. Our solid lines are sort of our truth here, the stochastic model. The dashed lines are the point cluster model, and the dotted lines here is the mean field model. So you can see the mean field model, all of them have the same initial slope. But you can see the point cluster model here, so it goes 2, 10, and then 50, 250, and 1, 250 are all on top of each other here. You can see it gets closer and closer to the truth of the stochastic model there as things go, as we increase the system size. So that's good to see. And the reason the mean field model just goes straight down here is it's not dealing with the clustering behavior, which is then the clustering, they start to correlate and they start to reduce, starts to stop the velocity variance going down because the particles are no longer interacting, you just they interact much more slowly. Then this gives us, so then I've just done the same thing here, but now looking at the relative error between the point cluster model and the stochastic simulations. So just to show you that we can see the relative error decreasing. That's good. Right. One more thing here, you can see that the time to reach a certain amount of error scales roughly as n to the half, which is we can understand sort of exactly how long you expect this model to be working for. Just to finish off, what we then decided to do is to think, okay, so for the PDE methods, the mean velocity is always 0 because it's just dealing with the overall distribution rather than individual simulation. But for the stochastic and particle simulation, the mean velocity of an individual simulation is non-zero. It's just that the overall mean approaches 0. So what we do, and the distribution of their means is get from the limit theorem. What we do is we change the initial condition of our simulations to test the centered uniform initial condition. So what this means is we take our sample in our stochastic case and then we shift it so that the mean is 0. And what this does is it effectively allows us to compare against the within sample variation rather than the difference in the means of each of the samples on the way through. Which you might think, okay, is that just bunching it all the way through? But we could feasibly reintroduce this intra-sample variation later on. That's sort of well defined if we wanted to do that on the way through. So basically we're just saying, okay, let's define a different initial condition like this. And then we effectively have to recompute what the effective initial probability distribution is for the PDE to compare that. And it turns out, as I think you can guess, it turns out it makes it better. So when we do this, we can see that our point cluster model converges much more quickly to stochastic solutions here. So they're all sort of on top of each other along this line here. In this case, the variance of the stochastic simulations is now approaching from below because we've removed a lot of their variance by shifting all the means to be on top of each other. So that's there. Now we can look at the error here. We can see the error here now up to sort of reasonable times once they've started clustering. We're sort of at like for 1250 at like 5% error, up to 10% there, which is a lot better than it was before when we had the non-centered case. And also the error reduces further if you define your velocity variance based on cluster instead of by particle. This sort of effectively what this says is if you, because we're predicting the big clusters, the more clustering that happens, the more correlation there is and the worse we predict it. So the big particles are predicted worse, and if you only count by a cluster, by the number of particles in the cluster, then you weight the big clusters less and it ends up getting less error. But effectively, that's just to say that the more clustering that happens, it eventually gets worse. But that's sort of where we're actually looking at the next steps of this model is the reason the more clustering happens is this model doesn't take into account the intra-sample correlations. For example, with a two-particle case, our models like the ones at the top where we just have a distribution going in. So this is like particle 1 velocity on the x-axis, particle 2 velocity on the y-axis. So there's no correlation at all in the model here, whereas in reality they're all very highly correlated. So we've done some bits on that, but I'll leave that for now. There's like ways of then maybe doing a model that involves the P2 equation instead of the P1 equation, which might then allow you to keep track of these. That's all. Thank you.
Very much. Any questions?
Do you know if this is related to these coagulation equations and Smoltovsky equation? Because I mean, the microscopic model is kind of similar, at least qualitatively. I don't know if there's numerical evidence that this, at least qualitatively, also looks the same.
I have seen simulations which qualitatively look the same. I haven't like explicitly investigated that, but yes, the end results of what you get out from this when you get the sort of distribution of the number of clusters or the cluster size distribution does look pretty similar to what you would get from the Smoltovsky equation, things like that. So it's, yeah, but you're right. That's an interesting thing to think about, it, whether this like could be used as a microscopic derivation or something like that. Yeah, I haven't thought about that explicitly. That's a good point.
And maybe also stochastic models for the Smoltovsky. I don't know if they exist or you might invent them. I don't know.
I think I've seen one of them, but that was more like a stochastic model. I don't think it started from the microscopic case. It just was like we assume that there is some interaction rate, which we can then stochastically evaluate. But it might be interesting to take that from a microscopic case.
Questions.
Oh no, go ahead. So in your derivation with method asymptotics, you are doing a kind of baby case of very short interactions, the hard sphere and hard sphere interactions. How would this fit into your framework, or would this be kind of be totally obvious?
I think I'm trying to think whether that actually fits in explicitly on the way through there. If you were to find for the clustering framework.
Or maybe just first, maybe even for the Boltzmann equation. Yeah. So
I think in the hard sphere case, the asymptotics still work quite similarly, except you now have like, rather than having our kind of loose short range potential, you just have a very specific radius at which everything happens. But I think the effective sort of the effective result on the way through is that the interaction happens between pairs of binary particles, and from the perspective of the outside system, all you see is an interaction and an output. So basically, the sort of key mathematical result at the end is that you split your system into a small scale where you have to then care about exactly what happens between two particles, and then from the outside, all you have is an input and an output of this small scale interaction. So if you were to do a hard sphere case, it would just modify what happens in this small scale bit there. I think.
Yeah, I'm just interested if you would be able to see this, or if these kind of connections would then be entirely, or if you could do something explicit, or because some way the dynamics are very explicit. Yeah, so
I mean, I haven't thought about whether that would come up with something explicitly nice at the end there. But you could definitely numerically do it getting this, and presumably that in the hard sphere case there may be analytic results that you could get about that. But yeah, I think that's an interesting. I think the interesting thing is we've got the general framework now, which you can then plug in different kinds of local interactions to see what that comes out with.
I guess I'm just curious about the efficiency of your method, right? Because it looks like this point custom model is very complicated to solve numerically. So how does that compare with actually just solving the stochastic problem?
Yes, that's a good point actually. So for the kind of range that we're looking at, it's sort of around sort of 250 particles where it starts to become more efficient. Then, right? It depends for the stochastic model exactly how. It depends exactly how far you want the distribution to have converged for the stochastic case, because the point of the point custom model on the way through doing it as a PDE model is you only have to run it once, I guess. But I mean, I guess then I suppose you also have the thing of how detailed you want your grid size to be. In terms of the keeping them sort of accurate to the to roughly the same, it was roughly around 250 particles that it was more efficient than the stochastic case for my notations on the way. I would necessarily claim that it wasn't possible to implement the stochastic one there or some case. But in general, because the reason we're doing this and the reason we like hope this is somewhat useful is that because it doesn't, it only scales with your grid size and not with the number of particles, because it sort of abstracts away the number of particles. So as you increase the number of particles, it's going to scale a lot better than the stochastic model for because then you have to start dealing with a lot more interactions there. So the idea being that like at some point for a large number of particles it becomes more efficient. But yeah, it is a good point, because for these lower ones, I was definitely like, may as well just use the stochastic for this case, because it's at the end it's obviously better and easier all the way through there. But yeah, it's primarily that we were trying to make it useful for smaller systems as well, but as it turns out from these results here, you really need to take more care about the correlations in smaller systems. And again, a stochastic model in this case appears to potentially be more useful for them anyway. That's good.
It might be a stupid question, but so why does it seems to me that your equation improves as n gets larger? Is there a reason for this?
Yeah, so it's effectively what I think is going on there is it's like the primary reason we're saying it's not working is that when these particles interact, they end up a little bit correlated, and we're taking our sort of Schwarzschild sense that maybe they're always uncorrelated when they're approaching new interaction, there's no effect of that. So the more correlations that happen, the more wrong it's going to be. And then when you have a bigger system, the effect of each individual correlation is smaller, because you've got more other particles bumping into each other correlating way through like that. So it's like it's sort of diluted out the effects there on the way through. Which again is why, yeah, so for small systems you have to use some higher order correlation model or just a stochastic model. So, but yeah, it's unfortunate in a way, but I guess it means the use case of this model is for larger systems where you have where that then becomes less relevant.
Okay, so if not, let's thank Calum again for the great talk.
Yes, that's it.